Imagine the coordinate system as a flexible rubber sheet where every intersection represents a point in a dataset. A matrix is not just a table of numbers, but a specific set of instructions that tells this sheet how to stretch, rotate, or compress. In a two-dimensional plane, we track the standard basis vectors, labeled I hat and j hat. Every matrix transformation is defined entirely by where these two unit vectors land. Their new positions become the columns of our matrix. Linearity requires two strict rules. The origin must remain fixed at 0, 0, and all lines that were parallel and evenly spaced must remain parallel and evenly spaced after the transformation. This consistency allows us to predict the movement of every point.
When we multiply a vector by a matrix, we are essentially asking where a specific point ends up. The output vector is a linear combination of the matrix columns, scaled by the components of the input vector. A diagonal matrix with values of 2 and 2 doubles the size of space in all directions. If the values differ, such as 2 and 0.5, space stretches along one axis while compressing along the other. Shear occurs when one basis vector remains stationary while the other moves parallel to the opposite axis. Visually, this looks like pushing the top of a square while the base stays glued to the ground. Rotation matrices use sine and cosine functions to move basis vectors along a circular path. This transformation preserves the length of all vectors and the angles between them, keeping the grid perfectly rigid but tilted.
Applying a rotation followed by a shear is equivalent to multiplying their respective matrices. The resulting matrix represents a single complex warp that encapsulates both operations in a specific sequence. Matrix multiplication is not commutative. If you shear space and then rotate it, the result is completely different than rotating first and then shearing. The order of transformations dictates the final geometry of the world. The determinant of a matrix tells us the factor by which areas change. If the determinant is 6, a unit square in the original grid will occupy 6 units of area after the transformation. A negative determinant indicates that space has been flipped over, like a mirror reflection. While the area scales by the absolute value, the orientation of the axes is reversed, changing the right-hand rule.
When the determinant is 0, the transformation squashes space into a lower dimension. A two-dimensional plane might collapse into a single line, or even a single point, meaning information is permanently lost. The rank of a matrix describes the number of dimensions in the output. A rank of 1 means all vectors land on a single line, regardless of where they started in the original two-dimensional space. The null space consists of all vectors that are crushed into the origin during a transformation. If a matrix collapses space into a line, an entire line of vectors in the original space becomes 0. The column space is the set of all possible landing spots for our vectors. It represents the span of the matrix columns and defines the reachable territory within the target coordinate system.
The inverse matrix acts as an undo button. It performs the exact opposite warping, pulling the grid back to its original square configuration. This is only possible if the determinant is non-zero. Matrices with a 0 determinant are called singular. Because they collapse dimensions, we cannot uniquely determine where a point came from. Mathematically, the inverse does not exist because you cannot expand a line back into a plane. During most transformations, vectors knock off their original paths. However, eigenvectors are special directions that stay on their own span. They might stretch or shrink, but they do not rotate away from their line. The eigenvalue is the factor by which its corresponding eigenvector is scaled. An eigenvalue of -1 means the vector stays on its line but flips to point in the opposite direction.
To find these stable directions, we solve the characteristic equation, where the determinant of the matrix minus lambda times the identity is 0. This identifies the scaling factors that leave directions unchanged. Diagonalization is the process of changing our perspective so that the basis vectors are the eigenvectors. In this coordinate system, the matrix warp becomes a simple, independent scaling along each axis. A change of basis matrix translates coordinates between different viewers. One person might see a simple rotation, while another sees a complex combination of stretches, depending on how their own grid is aligned. Symmetric matrices are guaranteed to have eigenvectors that are perpendicular to each other.
Their transformations represent a pure stretch along these orthogonal axes, making them fundamental in structural engineering and physics.
Orthogonal matrices have columns that are all unit vectors and perpendicular to one another. They perform transformations that never change the shape or size of objects, only their orientation in space. Singular value decomposition proves that any matrix transformation can be broken into 3 steps: a rotation, a scaling along the axes, and another rotation. Every complex warp is just a sequence of these basics. The trace of a matrix, the sum of its diagonal elements, is also the sum of its eigenvalues. It provides a quick measure of the total stretching happening across all dimensions simultaneously. Projection matrices act like a spotlight, casting the entire world onto a subspace. In a projection, every vector is moved to its closest point on a line or plane, effectively removing certain dimensions.
When projecting onto a line, the matrix ensures that the difference between the original vector and its projection is perpendicular to that line. This is the geometric basis for linear regression. Householder reflections flip space across a specific plane. They are used in advanced numerical algorithms to zero out parts of a matrix, making complex calculations much more efficient and stable. While we visualize in 2 or 3 dimensions, matrices can warp space in hundreds of dimensions. In machine learning, these warps represent transformations of high-dimensional data features into a recognizable pattern. Standard matrices cannot perform translations because the origin must stay fixed. By using homogeneous coordinates and adding an extra dimension, we can perform translations by shearing the higher dimensional space. Multiplying a matrix by itself repeatedly shows the long-term evolution of space. If the eigenvalues are less than 1, the entire grid eventually collapses into the origin as the warp is applied over and over. Markov chains use matrices where each column sums to 1. These transformations move the density of probability across the coordinate system until it reaches a steady state, visualized as a static distribution of points. A covariance matrix describes the spread of a dataset. The eigenvectors of this matrix point in the directions of maximum variance, effectively showing how the data is stretched through feature space. Linear differential equations treat matrices as velocity vectors for space itself. Instead of a single jump, points flow along curved paths dictated by the matrix, revealing orbits, spirals, or straight-line escapes.
In quantum mechanics, unitary matrices warp complex vector spaces while preserving the total probability. These transformations represent quantum gates, where the rotation of state vectors determines the outcome of a computation. Modern graphics processors are specialized hardware built specifically to perform these space warps billions of times per second. Every frame of a video game is the result of massive matrix multiplications occurring in parallel. Singular value decomposition is used in image compression by discarding the least significant space warps. By keeping only the primary scaling factors, we can reconstruct a recognizable image using a fraction of the data. From the rotation of a robotic arm to the spread of heat in a metal plate, matrices provide the universal language for spatial change. They turn the abstract concept of transformation into a concrete numerical reality.
Understanding matrices as active space warpers transforms linear algebra from a dry set of rules into a vivid geometric intuition. When you see a matrix, do not just see numbers, see the movement of the universe.